Okay, moving on to page 3 of the practice exam. So the first 2 pages there kind of drew from chapter 7, electron configuration, quantum numbers, light, atomic properties, etc. So not surprisingly, there's going to be a fair amount of material from chapter 8 here as well. So problem number 6 here, we want to draw some Lewis structures for the molecules or ions provided. So I did leave some space here to try to do it on the page. We'll see if I can fit them. If not, I'll just jump to another piece of paper, but keep that in mind when you're working these on your own. This is not the level of space I would probably leave on an exam for you here, but just starting with A, 2 hydrogens, a carbon, and an oxygen. So hydrogen can't be kind of in the middle of the molecule because it's only going to make one bond. Carbon is less electronegative than oxygen, so I would start with the skeleton with carbon in the middle, connect the other atoms to it. There's 1 valence electron from each hydrogen, so that would be 2, plus 4 from carbon would be 6, plus 6 from oxygen would be 12. We used up 6 already. That means the other 6 should start out on the oxygen, right? But from there, we'd probably recognize, well, oxygen has an octet, but carbon doesn't, so I should share those 1 pair of those electrons in to make a double bond. So there'll be a double bond between carbon and the oxygen, right? But then just single bonds to the hydrogen. That would be the appropriate structure. We've satisfied the octet rule on the carbon and the oxygen, right? And the hydrogens just need 2 electrons. And we'd also have 0 formal charges on the carbon and the oxygen, which is something we're looking for definitely in having the right structure, is minimizing formal charges. Okay, moving on to B, H2O2. So we should recognize here, hydrogen, like we said in the first example, can only make 1 bond. So we don't want to put any hydrogens in the middle. That means the oxygens would have to be connected to each other, right? And if we're thinking about formal charges, we'd kind of be looking for our oxygens to only have 2 bonds in our final molecule. So if that's the case, we can only put 1 of the hydrogens on each of the oxygens, right? So there's another possible structure you could draw, or at least possible skeleton, where you put 2 of the hydrogens on 1 oxygen and none on the other, but that would not lead you to good distribution of electrons, octet rule, formal charge, etc. So this is the structure we should come to if we're thinking about all those issues we brought up. Now, total electrons, 1 again from each hydrogen would be 2. 6 from each oxygen would be an additional 12. That would be 14. We used up 6. That means there's 8 left. But look at that. Each oxygen needs 4. So we can put 2 non-bonding pairs on each oxygen. That would satisfy the octet rule for both oxygens. Also get both oxygens to 0 formal charges. So that would be a good structure there. Part C, C2F6. Fluorine, very similar to hydrogen, right? We only ever want to make 1 bond to the fluorine. Now, fluorine is going to be different because we do need 8 electrons instead of just 2, right? But that should lead us to kind of start our skeleton with the carbons, because we want the fluorines to be around the outside of the molecule. Now, each carbon can make 4 bonds, right? In fact, if you're keeping your formal charge rules in mind, we want to try to make 4 bonds for each carbon, so we can distribute the fluorines around the carbons in that manner, where each carbon now has 4 bonds, so that will end up being good for the carbons. Now, total electrons here, 4 from each carbon would be 8, 7 from each fluorine, so 7 times 6 is 42, plus 8, 50 total electrons here. Now we used 2, 4, 6, 8, 10, 12, 14. That means there's 36 left. Well, we need 6 for each of those 6 fluorines. That would account for all 36. Now, that's a lot of dots to draw in here, but right, when I go to grade these, I want to see every single dot that should be there. And be careful about erasing as well, right? Because if you erase and you don't erase completely, and there should be 6 dots, but it kind of looks like maybe there's 8, right? That would have to end up being counted as an incorrect structure. So it's often better to redraw when you decide to move electrons instead of erase, kind of like I did on the first one, right? Maybe make a little arrow, but then draw the structure that would result. Okay, D is a little different here because it's not a molecule, it's an ion. It's got a charge. We'll have to account for that charge in the electron count. So maybe this one I'll write out a little more explicitly how we get to the right electron count. The arsenic here is less electronegative than oxygen. That should start in the middle. Right? And we'll connect the 3 oxygens to the arsenic. Now, as far as electrons go, arsenic, 3 oxygens, right? And in this case, we also have to account for the charge. So if you're not familiar with arsenic, it is underneath nitrogen and phosphorus, right, in the periodic table. That means 5 valence electrons, 6 for each oxygen. Now, because of the charge, -3 charge means there are 3 additional electrons there than just what would come with the neutral atoms. So that would be, say, 18, 21, 26 total electrons here. Now, we used 6 already. We can use up 18 of the remaining 20 by completing the octets on the oxygens, like so. Right? And that'll leave 2 left that would have to go on the central atom here because we can't go past 8 on oxygen. That's oxygen is too small for us to extend past the octet. Now, if we start to evaluate the structure, like we should do once we get the electrons in there, we did satisfy the octet everywhere. We have negative formal charges on all the oxygens. It'd be 6 minus 1 minus 6 for every oxygen there. For the arsenic, 5 minus 3 minus 2, that's a neutral formal charge, so that is all good. And since this is a -3 ion, there do have to be 3 negative formal charges overall in the molecule as far as the algebraic total of charges. So -1, -1, -1, and 0, that is the best we could think about doing in terms of formal charges for that ion. So that is an appropriate structure. Okay, now E, H2SO3, that's an acid, right? And we've talked in some of the other reviews that we've done, the structures for acids can be a little tricky. I think the best way to approach drawing the structure for an acid is to start with the structure of the appropriate polyatomic ion the acid is based on, which in this case would be sulfite. So if we start by trying to draw sulfite, wherever the negative charges are in sulfite is where the hydrogens belong in the acid. So if I draw sulfite, 6 for all of the atoms involved would be 24, plus another 2 is 26, right? So this ends up looking a lot like the structure we just drew, because when we put all the electrons on the oxygens, we have 2 left on the sulfur in the middle. So very similar to what's going on here, right? Because the arsenic, while having a different number of valence electrons, that's accounted for in the charge, the exact same structure. In this structure, right, we have negative charges on the oxygens, right? But the way this one is, there's actually a positive structure on the sulfur as well. Sulfur is 6, or in this case, -3, -2. So we probably wouldn't stop here. We'd probably make 1 double bond to minimize the formal charges. Now, if we were just drawing sulfite, we wouldn't stop with just making 1, because this would be a case where there are resonance structures, and we would want to draw all 3. But since we're trying to draw the acid, all we really need to know is where are some of the negatives in the molecule. And right there are the 2 negatives. That's where the hydrogens should be bonded in the acid. So from there, I can finish the structure for the acid just by putting those 2 hydrogens in as if they were attached to those oxygens. Now, those oxygens would not be negatively charged anymore because, right, H plus is what's characteristic of the properties of an acid. That means 2 of the electrons that made the oxygen negative are now used in the bond to the hydrogen. So that would be our structure for H2SO3. Okay? And there aren't resonance structures here because atoms. The resonance structures, the rule is the electrons can move around to different places, but the atoms all have to be in the same place. Putting this hydrogen over here on this oxygen, that would be moving atoms. So there's only 1 resonance structure there for that H2SO3 sulfurous acid. Okay, 1 more here in number 6. So F, C2H2. So similar there to what we talked about earlier for like the peroxide, part B in the problem. Hydrogen only being able to make one bond. We want to start with the carbons here when we draw the skeleton, and the carbons should be connected. Right? The best place is to put the hydrogens on each carbon. Right? If you try putting two hydrogens on one carbon, you'll actually end up with an untenable structure, right, that won't match the rules very well. So that's an avenue you might have to go down if it's not a structure you're familiar with. So if you're struggling with how did I make that decision, you might try out that structure and see what happens when you try to finish it. But from this skeleton, there's 8 electrons from carbon, 2 more from the hydrogens is 10 total. We've used 6. So we might start like that, putting 2 on each carbon, right? But that doesn't get the carbons to where we want them to be. They only have 6 electrons there total shared. So both of these should actually be bonding electrons that are shared between both carbons. And that would give us the structure with a triple bond between the carbons, which would satisfy the octet rule and get us to 0 formal charges on the carbons. Okay, the next question is also Lewis structures, but the video is getting a little long, so we'll have to do those in the next video.